Hello, everyone. Mr. Hine, and I am back. And we're talking about 552, finishing up 55, and really building off the last lesson where we made a big observation, and now you get to learn what the observation means and the name of it. Now, maybe you see it by the title of L'Hopital's rule, but let's explore it and what it means. So, here we go. So, 552. So, before I get into this, recall what the last video is about in case you forgot or the last lesson. And the idea of the last lesson is, say we look at a limit, such as the limit as x approaches 0 of sine of x over x. But the idea there is that we can't just substitute in, because if you substitute in, you're going to get sine of 0 is 0 over 0. And that's a problem. Because if you get 0 over 0, remember that that is what's called an indeterminate form. Right? So we can't substitute. So our way around that was we did two approaches, where method one was the graph, in which we saw that on a graph of this, it looked something like this, where at 1 there's a hole, but the graph looks like this, where the limit as you approach from the right is the same as you approach from the left, which therefore is equal to 1. And we got the answer that way. And then what we also did was we looked at it through a second method, an observation, where we looked at this original limit as breaking up the numerator and the denominator of the rates. So then we did, what's the rate of sine of x as x approaches 0? And we compared that to the rate of x as x approaches 0. And what happens is, if you looked at each function separately, they were almost identical. So that's sine of x, that's x. But as you approach 0, they were identical, which implies that the ratio was 1, which therefore checked our answer. So where we left off on the video, where we left off at 5.5.1, was the idea that the limit as x approaches 0 of sine of x over x, we think we can get that by calculating the rate of, well, I'm going to even skip that step. Remember that we could do it by doing the rate of the top divided by the rate of the bottom, but remember, the rate is the same thing as just looking at the derivative. So d dx of sine of x. I forgot to write the limit, so I need to erase that. But it's equivalent to saying, look at the limit as x approaches 0 of the derivative of that function, the rate, and compare that to the limit as x approaches 0 of the rate of the bottom function. And that's where we left off. And this right here is huge, because this is actually, although we just observe it, that is actually a true thing. And that is what's called L'Hopital's rule, named after the French mathematician. And I pay homage to their culture and his name, so it's a lowercase l. I don't know French, but there's that symbol above O, and I want to write it as it should be written. So, L'Hopital's rule, and this is important, give it 4 stars. This is a skill that helps us solve problems, unique situations. So again, we learn so much tools, so every problem that we encounter, we have an approach for solving. And what's L'Hopital's rule says? It says here that if the limit as x approaches a for some value a of f of x over g of x equals 0 over 0, or infinity over infinity, which again is just some indeterminate form. So if this is the case, well, then what we can do is we can calculate this limit by doing the limit as x approaches a. So the limit stays the same, but we look at the rates of these two, which is just the derivatives. So we can just look at the derivative of that, and that's the same problem. And that is L'Hopital's rule, and that's very powerful, and that helps us. So let's look at a few examples to help you understand this in practice. So let's do that original problem that we did last lesson and in this beginning, and see how it equals 1. So notice if we try doing this, we get plug in 0, we get 0 over 0. So therefore, we can apply L'Hopital's rule, which then says that this is equivalent to doing the limit as x approaches 0 of the derivative of sine of x. And the derivative of, well, I'm just going to write it out at first. I won't do it moving forward, but for this first time. So then that's the same as saying the limit as x approaches 0 of the derivative of sine of x is cosine of x. And the derivative of x is just 1. So we can get this answer by evaluating this limit, which is going to equal the limit as x approaches 0. Well, if you plug in 0, cosine of 0 is 1 over 1, and there's your answer 1, which checks out with what we got in the previous methods. And there's L'Hopital's rule. And you know, it kind of makes sense, L'Hopital's rule. The idea is that if we look at the rate of the functions as you approach the limit, well, that's going to equal the same thing as just the functions themselves, because the way at which a function is approaching a point, the rates are going to be identical of the functions. Well, I guess not necessarily. So it's a pretty powerful thing. So let's keep going. More examples. Example number 2. Example 2 says, limit as x approaches 0 of cosine of x over x minus 1. All right, now I threw this one in for a reason. So let's try plugging this in. So if we plug it in, cosine of 0 is 1 over 0 minus 1 is negative 1, which actually is equal to negative 1. So notice there's no need to apply L'Hopital's here, because we never got an indeterminate form. But what if you try anyway? What if it's like, hey, Mr. Hein, I know we didn't need to, but let's try it anyway. What if we tried it? Can we still use it? Can we still use L'Hopital's rule? Is the question, and still get negative 1? Well, let's find out. If we did the limit as x approaches 0, and we take the derivative of the top, which would be negative sine of x, over the derivative of the bottom, which is just 1, and then we evaluate this limit, well, sine of 0 is 0 over 1, which gives you 0. And there it is. So notice, it's not, you can't apply this rule. You can't apply L'Hopital's if not an indeterminate form, if not a limit of an indeterminate form. So it only works if you get 0 over 0, infinity over 0, or again, technically 0 infinity or infinity over 0, but you won't see that too much in this class. Let's look at two more examples, and then I'll wrap this up. Example 3, the limit as x approaches 0 of sine squared of x over x. All right, we evaluate by substituting. Sine of 0 is 0, so if we square it, we still get 0 over 0, so therefore we can apply L'Hopital's and get the limit as x approaches 0 of the derivative of the top. Now this is chain rule, so it's the derivative of the outside, 2 comes in front, leaving the inside alone, times the derivative of the inside, and the derivative of sine of x is cosine of x. And then we take the derivative of the bottom, which is 1, and we ask ourselves, can we evaluate this limit? Well, if we substitute in 0, you would have 2 times 0 times 1 over 1 gives you 0 over 1, which equals 0. So therefore, there's our answer. And that's great. Thank you, L'Hopital, for making my life easy. And the very last example, let's do the limit as x approaches 0 of 1 minus cosine of x over x squared. Okie dokie. Plug in 0, we would get 1 minus 1 over 0 squared, which gives us 0 over 0. So therefore, by L'Hopital's rule, we can evaluate this by looking at the limit as x approaches 0 of the derivative of the top, which the derivative of 1 is 0, the derivative of negative cosine, well, the derivative of cosine is negative sine, so you have negative sine, which will just be sine of x, over the derivative of x squared, which is 2x. We evaluate this, which plugging that in, sine of 0 is 0 over 0. Well, notice we got an indeterminate form, so again, we can apply L'Hopital's. So let's put here that we applied L'Hopital's. This again, since we got 0 over 0, we can again apply L'Hopital. So that is, you can apply it multiple times. It doesn't prevent us. The rule still holds since we got the limit of an indeterminate form to be 0 over 0. So then we can do the limit as x approaches 0 of the derivative of sine of x, which is cosine of x, over the derivative of 2x, which is 2. Evaluating this limit, cosine of 0 is 1 over 2, and there's our answer. And there you have it. So there's a very powerful approach on evaluating limits of indeterminate forms. Now that's not to say that you can't use this graph. That would work. But graphing sometimes is a little bit slower than if you just know the trick with algebra. And L'Hopital's rule is very, very powerful, and it helps us in these types of problems. All right. Hope that makes sense. If you have any questions, make sure to stop by Office Hours with us. All right. Bye-bye and good luck.